there we go, we're live. So, I'm going to start today, before I hit today's lesson, by just going back to yesterday's lesson and pointing out, can you go back to your notes from yesterday? And I made a brutal algebra mistake here. Egats, this is embarrassing. Look at that. So I had the inequality negative 5 plus 8x is greater than 0. And let's see, am I on here? And right, yeah, this inequality right here. And right there, everything's good here. And then right there, I added 5 to both sides of the equation, but then somehow it still stayed a minus 5. Yeek. Can you go back? Okay, so erase that, or just cross it out if you wrote in pen, and erase that. And then I didn't even notice it when I rewrote it down here, so erase that, which means that this would be here, and there we go. So there we go. So that was example 1 from yesterday. Brutal typo, righto, mistake-o. Okay, so there we go. Tidy up our notes from yesterday. Okay, so that's it. And of course, the main idea from yesterday is, of course, we just looked at functions and we found a way to factor the function so that we saw what the factors were, and that gave us the points. Of course, your factors, when you set your function to equal to 0, your factors become your x-intercepts. Or in this case, your factors become, since this is the derivative, your factors become the places where the slope is 0. In other words, the places where you have a tangent to the curve, or a horizontal tangent to the curve. And that kind of breaks your function down into intervals. And those intervals then, you explore whether your function, or the derivative of your function, is positive or negative within those intervals. So that tells you if your function is positive, if the value of the derivative of your function is positive over an interval, that means the original function is increasing, and if it's negative, it's decreasing. So that's basically what we did yesterday. That was yesterday's 4.1 lesson. Today we're going to start 4.2, and 4.2 might take us more than one class to kind of get through. In fact, I kind of know it well, especially since I'm going to slow down a little and do a quick grade 12 review question. Now, those of you who haven't done the grade 12 40S course yet, you haven't seen this before, but it's not overly difficult. This is an example straight from the grade 12 notes, so it'll be a bit of a blast from the past for some of you. And let's just work through it really quick. Determine the roots of the following function. Okay, so what does roots mean? That means the x-intercepts. That means I set my equation to 0. Oops, there we go. Set my equation to 0. Oh, I lost a negative already. And we're already kind of stuck. Can I factor this thing? Well, no, I can't. So the factor theorem tells me that any value for which you plug it in for x and the right-hand side is 0, that has to be that means that x is a 0, or an x-intercept of the function. So basically, we just guess and check. If this thing has integer factors, then those integers have to be factors of negative 4. And negative 4 has the factors plus or minus 1, plus or minus 2, and plus or minus 4. So the first one I'll try is 1, and 1 works right away. So p of 1 is actually negative 1 cubed plus 4 times 1 squared plus 1 minus 4. And as you can see, that does make 0. So p of 1 is 0. Therefore, x minus 1 is a factor. And then from there, so if I know that factor, from there I can find more factors by doing something that we did at the very beginning of the course when we reviewed some grade 11 and 12 algebra. We can long divide x minus 1 into here to find the rest of the factors. So I'm going to long divide this and find the rest of the factors. So x minus 1 goes into here, and minus x squared times. So minus x squared times x minus 1 is minus x cubed plus x squared. I'm subtracting that. So that's going to be negative x cubed minus negative x cubed. Those go away. 4x squared minus an x squared is 3x squared. Bring down the plus x. x goes into 3x squared 3x times. And 3x times -1 is -3x. I'm subtracting that. So that's 4x. And this had better not have a remainder, or else something's wrong with what I've been doing, and it doesn't. So that's 4x minus 4, which is 0. So my other factor, I'm kind of out of room here, I'll move over. So my other factor here is that I have x minus 1, and I have negative x squared plus 3x plus 4. Okay? So again, if I set this equation to equal to 0, that'll give me the x-intercept. And I can divide both sides of this equation by -1. That makes this easier to factor. And then I can factor this. What two numbers times to make -4 and add to make -3? -4 and +1. And there we have it. We have our x-intercepts. We have that x is 1, 4, and -1. So there we go. We found the roots of the following function. The y-intercept's easy. The y-intercept happens when x is 0. So basically I want p of 0, which is going to be -4. And then we kind of put all of the information we now know about this function into this chart to kind of check out, sort of summarize our knowledge of this function. So its degree, let me write it down again. It is p of x is equal to -x cubed plus 4x squared plus x minus 4. Okay, so there's what we know about it. Its degree is it's a third degree polynomial. Its leading coefficient's a -1, which tells me that because it's a cubic, I know that it has one arm that goes up forever and one arm that goes down forever. And because the leading coefficient is -1, I know that that means that the left arm is going up and the right arm is going down. And that's basically the same thing as its end behavior. Its end behavior as x approaches infinity, y approaches -infinity, and then as x approaches -infinity, y approaches +infinity. My zeros, I just found them, my x-intercepts. That's how good my memory is. What were they again? 1, -1, and 4. So plus or minus 1 and 4 are my x-intercepts. My y-intercept is -4. And then I can make an interval diagram. And my interval diagram I can make by just factoring this thing. So now remember, this thing factored into, well, the first factor I found, here, let me make that prettier. The first factor that I found was, what was it again? X minus 1. And then the other factors that I found were, so x minus 1 was a factor. And then, you know what, actually, now that I think about it, I should put the negative out front. Remember that negative that I divided both sides of the equation by? Well, that is a factor. So x minus 1 was the first factor I found, and then x plus 1, and then x, what was the other one? Oh yeah, oops, go away. And then x minus 4 was the other factor. So there we are in factored form. And now that we're in factored form, we can make an interval diagram. And we did one of these just yesterday, right? So this chart doesn't give me much room. But okay, so for the interval, let's see, so my zeros from these factors here, of course, are -1, 1, and 4. So we'll make the same kind of diagram we made the other day. If you didn't do this kind of diagram this way in grade 12 when you did this course, it's not really that different, no big deal. So intervals, and we'll make sure we'll kind of do this the same way, and then we'll list our factors. So x, okay, well there's actually there's a -1 out front here, so we got to kind of deal with that. So there's a -1, then there's an x minus 1, there's an x plus 1, and there's an x minus 4. Okay, so in our intervals, our first interval goes from x is from -infinity till x is, let's see, less than, what was the smallest one? I guess the smallest one, the first one would be the -1. So pick a number smaller than -1. How about -2? All right, so if I pick an x of -2, well, -1 is still negative, but this here is now going to be -2 minus 1, which is a negative. Oh, I meant to be black. There we go. And then the next factor is -2 plus 1, which is still a negative. And then the next function is, or the next factor is -2 minus 4, which is still a negative. So I have a negative times a negative times a negative times a negative, which overall, and I don't have an overall yet, is positive. Okay, so the function is definitely positive for the first interval. For the second interval, when x is between, let me write that better, when x is between -1 and 1. Okay, the logical number to pick between -1 and 1 is 0. So 0 doesn't affect the factor -1, that's still negative. And 0 minus 1 is negative, and 0 plus 1 is positive, and 0 minus 4 is negative. So I have a negative times a negative times a negative, which is a negative. And then lastly, what happens when x is bigger than 1? So let's pick a number bigger than 1. Oh, actually, there's more than that. Sorry, there's another interval after that. So let's see. So when x is bigger than 1, again, the -1 is still negative. Pick a number like 2. 2 minus 1 is positive. 2 plus 1 is positive. 2 minus 4 is still negative. A negative times a negative is positive. And finally, now our last interval is, oh, this still had to be smaller than 4. Sorry, I forgot to put the other part of the interval. The last interval here is what happens when x is bigger than 4. So let's pick 5. -1 does not get affected by changing the x to 5, so that's still negative. 5 minus 1 is 4, which is positive. And 5 plus 1 is 6, which is positive. 5 minus 4 is 1, which is positive. And a positive times a positive times a positive times a negative is negative. So I now have a very good picture of this graph. So this graph is, I'm going to move and draw it someplace a little bigger here. This graph is, well, first of all, let's put down the zeros. The zeros happen at -1, 1, and 2, 3, 4. The y-intercept happens at -4. -1, 2, 3, 4. Okay, we know that in the interval less than -1, we are positive. So it's going this way. And we knew that, right? We knew that the terminal arm, we knew that the end behavior was as x approached -infinity, y was going up forever. Okay? We know that it goes down, and here is where, now I'm kind of assuming that this is where it turns around, because it looks like it should be symmetrical there, right? But do I actually know that that's the lowest point? And if anybody asked that of their grade 12 teacher when you were doing this stuff, they'd have said, well, you'll learn how to figure out whether or not that really is the lowest point when you're doing calculus. The same problem is going to happen here. I know that between 1 and 4, I know that my function is positive. But how positive is it? How high does this go? And again, if you asked your grade 12 teacher, some of you had me as your grade 12 teacher, it was, you know, are we going to get marked wrong if I go way too high or way too low on this function? And the answer is no, because right now you don't have the tool in your toolbox to figure out how high that point is. That's where grade 12 algebra kind of stops. So then after that, of course, in the interval when x is bigger than 4, we go down forever. So today we start dealing with that. How do we figure that out? You can probably already figure this out. We actually already have the tool in our toolbox to figure out how high and low those things are. You do know that if you draw a tangent line here, it will hit the highest point there with a horizontal line. And this, of course, will also be a horizontal line. And you know horizontal lines have slopes of 0. And what do you know about where the slope is 0? Think about that. We kind of already know this. So we're putting together something from earlier in the course to something from right now. Now, we actually do have to deal with some terminology here, too. Okay, so that's my grade 12 review. And that's as much of it as we're going to do. Look at that, I burned half a period just doing one grade 12 problem. Okay, so I told you this would take more than a day. So let's move on. Okay, oh, you know what I did for you guys? Just to see if maybe you wanted to try to save some writing or try to save yourself having to sketch diagrams. I mean, I don't know if some of you have printers or not that you want to use, but I actually put into your class notes. Let's see, who can I pick on here? Yibo, can I use you as an example? If Yibo at home right now, I better get the okay from Yibo before I open his file. Not that there's anything in there that would be weird. Okay, so if Yibo were right now to open his class notes file, and again, you can get to that by just going to class notes through Teams, right? Again, and I think I showed you the other day. If I didn't show you the other day, I'll show you again in a second. So here, I'll show you right now. Let me go to the Teams. Oh, I can't get to Teams unless I unfold this. Oh, this is a drag. There we go. Okay, if you go to Teams, and go anywhere in Teams, but mainly just go to where your Teams list is. Go to all Teams, and there you go. So go to this team, which is right here, and then if you go up to Class Notebook, boom. When you open that, you should be able to find the 3 files that I was just pointing out under Yibo's file. Notice I see all of them because I can see the whole class. But so Yibo there should have class notes, homework, and quizzes. And if Yibo clicks on class notes, right there, you'll see the notes that I've shared with you. And here's today's lesson right there, 4.2 maximum and minimum critical values. So if you open that and look at it, you'll see, aha, I can download for myself and print, if I don't feel like drawing so many notes, this as either a Word file or as a PDF file. So there you go. That gives you some options if you don't want to do a ton of notes drawing here. Okay, so anyway, okay, now let me get out of there and back to where we were. There we go. There we go. All right, so 6.2 is officially called maximum and minimum values. And altogether, values that are big and small compared to the rest of the graph are called extreme values. So the first definition here, for those of you who would rather write your notes, I'll slow down a bit, and extreme values of a function f are the local and absolute maximums and minimums. So the function f has an absolute maximum at 7. So this here is what we call the absolute maximum of this function, because it is the highest point overall. Absolute kind of means overall. F has an absolute minimum down here. So that's my absolute minimum. When f has a f of 4, when x has a value of 4 in this function, you have what's called a local maximum. And when f of x is 5, when f of x is 5, when f of 5 here, this here is a local minimum. Get it? It's not the overall minimum for the graph, but in that area, it's locally the minimum of the graph. And then f of 7 is both a local maximum and an absolute maximum, because it's locally in this area the maximum, and it's the maximum overall. So it's, you could also call it a local max. Okay, and you could, I guess, they didn't bother saying this, but you could actually call the 9.2, I don't know, can you call the 9.2 or the 2.1 local minimums? Not really, because they just happen to be the places where the graph ends because we restricted the domain of the graph. I don't really know if this is a point where, for example, it's going to turn around. Like, I don't know that, so I can't assume that it is. So it's not really a local minimum. It's got only a local minimum if it is a point where the graph gets that low and then turns around. So 9, x is 2 and x is 9 are, well, x is 2 is the absolute minimum because it's just the lowest point that the graph goes, but I don't think I'd call 9 2 a maximum or a minimum. That's why the notes don't bother saying it. So there's our new terminology. If we go back to the example we were looking at from grade 12, that's what we didn't know how to do. We didn't know how to find my local max and my local min. And you might be saying, well, isn't this an absolute max? No. How come this one's not an absolute maximum like the other one I was looking at a second ago? Because this function has an arrow. It's going to go up forever. There is no maximum to this function. It's going up forever. And there's no absolute minimum either. It's going down forever. So the words local are important. If you, in your work on some sort of quiz or test said, oh, I'm finding the maximum, I got to take off half a mark. The word local has to be there because this, you have to understand that this function right now doesn't have a maximum. The one down here does, right? Because it will never ever get higher than this point, and it'll never get lower than this point because I've restricted the domain. Speaking of restricting domains, let's take a look at example 1. So let's try to do what we just did on that first diagram here to example 1. Okay. What do we know? We know that we have no, oops, I meant to write no absolute maximum. How do I know that? How do I know looking at that graph that I don't have an absolute maximum? Oops. Right? Because of that. Because it's got an arrow going up. That thing's getting bigger forever. It's never going to have an absolute maximum. But I do have a local maximum when x equals -1. Okay. And now, how you say the local maximum doesn't really matter that much to me. You can say it's a local maximum when x equals 1, or you can say I have a local maximum at f of -1, if it is f of, oh, it's not f of x. Oh, okay. I guess we can't say that. This is only a y. So I wouldn't say that. I have a local maximum when at the point -1, and what's the y value there too? So if you said local maximum when x is -1 or local maximum at -1, 2, either one of those is a perfectly good answer. And that is, of course, this dot right here. Okay? What would I call that dot?
Absolute minimum.
I would call it the absolute minimum. In fact, I can call it both absolute and local minimum.
Wait, excuse me. So if you have an absolute, wouldn't that automatically make it a local minimum or a local maximum?
Yes.
So why would
So
you
the
need
way,
to...
well, because it depends on what kind of the nature of the function you're studying is and what you want to do with it. But it's kind of like, you know, it's kind of like all squares are rectangles, but not all rectangles are squares, right? All absolute maximums are also local maximums, but not all local maximums are absolute maximums. Does that make sense? Sorry, it's easy to get tripped up in the wording. Okay, so that's both an absolute and a local minimum at, what is that, at x equals 1, or at the point, you could say at the point, what is that, 1, -2. Okay, and of course it has an end point, whatever that thing is. Now, the only reason it has that endpoint is because, can you see this? There's a domain restriction. Oh, there it is. That point is -√3, right? And where does the -√3 come from? Well, it comes from the fact that if we wanted to actually do some math on this thing and find its intercepts, we'd have to go, okay, set that to 0, and then factor out the x, and then x, that means x is 0 is one of my points, right? One of my x intercepts. And x squared minus 3 equals 0 would give me my other one, and that would be x is equal to plus or minus the square root of 3, which is what that point is and that point is. Now, the minus square root of 3 happens to be, if you look up here, happens to be a restriction on my domain. So that's why blonk endpoint there instead of an arm going down, which is what this thing would normally have, right? Okay. It doesn't have a restriction heading the other way, going to the right, so that's why I have to put an arrow up here, and that's why I don't have an absolute maximum to this thing. Okay. So now we have the ability to go a huge step further in describing a curve than we could back in grade 12. We have the ability to figure out how high and low those curves tend towards between their intercepts. Okay. All right, I kept you a little later yesterday, so I'll let you go a minute early today. You can head out to music. That's a good place to stop, actually, after example 1 there. We'll pick it up there with example 2 tomorrow. I won't assign anything new, so if you're still working on the 4.1 questions, you can just spend some time tonight working on those. Don't go anywhere yet, though. I haven't downloaded attendance. Actually, even it wouldn't actually, now that I think about it, wouldn't matter that you did. It would just say what time you left. As long as I don't do something dumb like end my meeting before I do attendance, I think everything works fine. So there we go. Okay, so guys who have to head to music, off you go. Sorry I made you late yesterday. And there it is. We'll pick it up there tomorrow with more figuring out how to find the highest and lowest points on curves. Okay, and if anybody has any questions or anything, I'll leave the Teams meeting open for a few minutes, but I am going to stop today's video, and then we'll keep on adding to that video tomorrow. Okay.